Um, all right, so I'm really pleased to have Scott Duxbury here today. Scott, you were an alum of Social Networks and Health, if I remember correctly, back in the day, right? Didn't you come to this meeting once or twice?
I actually did not. No, I've always been on the periphery of this network and finally got into the course. So thank you for having me.
Well, I'm glad that was clearly our oversight then. So welcome to the club. It's a little like Hotel California. So welcome. In any event, Scott has a wonderful new book out on dynamic network analysis and statistical analysis of dynamic networks, or dynamic network data. I'm butchering the title. It's a Sage book come out, and he's nicely agreed to share some of his insights on what I think is one of the nicest new models for newish models for dynamic network analysis, which is the relational event model. And so all the work we did earlier on ergoms and some of the works on network autocorrelation that I just discussed were all in static networks. And what's beautiful about this is that it's taking some of those insights and moving them off to the dynamic frame. So Scott, I'm going to turn it over to you, and thanks for coming.
Thanks. Thanks so much, Jim, for introducing me and for having me here. So as Jim alluded to, today's lecture, or I guess follow up to the recorded lecture / Q&A, is on relational event models, or REM. So REM is a kind of interesting class of model. I think statistical network modeling is kind of, in some ways, it's almost the inverse of kind of our classical regression frameworks, in that the better quality data we get, actually, the simpler the final model becomes. Because as our data becomes more and more fine-grained, we're often able to work around the types of endogeneity and simultaneity issues that create all types of problems in ergom and cross-sectional models like that. So relational event models are kind of interesting in this regard, because if you read the texts and what's out there right now, your head's just going to be like, what is going on? This is so technical. This is so complex. But at the end of the day, what I like to think about with relational event models is actually, when it gets to the estimation stage and when we implement them, it's just a logistic regression or a Cox model. And so once we walk through these steps, what I'm hoping to get out of this is that you can look at the REM, and instead of being like, oh my God, this is the fanciest, newest statistical network model, I can never implement it, instead be like, it's a logistic regression. I'm going to go do this. I'm going to answer interesting questions. I can interpret it. I can apply it and work with it in a familiar way. So before we get into what REM actually is, I think there's this really careful distinction we need to talk about in terms of what type of data REM is appropriate for. So typically when we're looking at a longitudinal network model, whether it's a Siena model, whether it's a Tergum, whether it's a temporal variation of a network autocorrelation model, what we're typically assuming is network panel data. And network panel data is really unique for a couple of reasons. One is that we have imperfect information on time. So if we're thinking about this really classical example of the AdHealth friendship network, we have wave 1, we have wave 2. Students are interviewed over the course of 6 months, a year, something like that. The timing on the differences between the networks is really, really coarse. We don't actually know exactly when a tie changed or exactly how long it lasted. But by comparing between these snapshots, we can say, okay, there are differences, and we can start looking at the change process. And so the data on timing is coarse. We don't know it exactly. The second major distinction between relational event data and network panel data is that the tie itself is typically assumed to persist across time. So if we're thinking in the framework of a Siena model, and we're predicting whether actors are creating or withdrawing ties, if we're observing a tie at 2 time periods, we're only saying that that tie has gone away because an actor chose to withdraw it. We're assuming persistence between 2 observations. Now, in relational event data, we actually challenge both these assumptions, or we get a different type of data structure. The first major difference is the data is an event, hence relational event, right? It's an event that connects more than one actor. So if we're looking at something like an email exchange, this isn't something like I don't send an email and that email lasts until I withdraw it. I send it. That's the event. The email goes out. I'm waiting for your return. If we're going to drink beer together, it lasts as long as we're at the bar, right? It's an event. It happens. It has that moment in time. This session, right, is a half hour long. I get kicked out at the end of it. I'm not withdrawing. It has a finite time period. And so when we're looking at relational event data, the first thing we need to verify is that we have this structure. The tie has a precise, kind of well-defined temporal duration. It has its own time window, and it acts as an event connecting at least one actor. The second distinction with relational event data is we're assuming that we have really good information on the timing of ties. So in the classical model outlined by Carter Butts, this was originally conceptualized as like exact, like down to the second, down to the minute, down to the hour. But we're able to relax that assumption as long as we get approximate sequencing. So as long as we can recreate the sequencing of events, which happened first, who spoke second, who spoke third, and recreate the ordering, then we can work with this data and recreate the sequencing of events. So those are the two key characteristics of relational event data. We have a tie that has a short, kind of well-defined time window of duration. And second, we have good information on the ordering of events. Now, once we have those two characteristics, we can start working with the data. So I like to think with REM as essentially involving two steps. The goal of REM is to model the hazard or the frequency with which events are activated within time periods. We're working in an analysis that's very similar to a classical event history model. We can think about the coefficients as reducing the time to event occurrence or decreasing the spacing between repeated events. We can also think about it as increasing the frequency or the hazard ratio of events occurring within a particular time period. This means we're predicting kind of periods where I might be sending emails off back and forth like crazy. As the semester approaches, I'm going to be firing off those emails all the time. As summer comes along, my inbox is dead, right? These are the types of things we're looking at. So when it comes to actually formulating the model, what we do is we take the data. And usually for REM, what we want is a type of edge list format to start with. We have all the connections between actors stored in one column and a second column, senders and receivers, or if it's bipartite, first mode, second mode. And then in our third column, we have the time that the event occurred. Now, what we're going to do with that data structure is we're going to expand it. Rather than simply looking at the edges that exist, we're going to recreate all possible connections that could have existed and then compare them to the ones that did not. And so in this respect, what we're taking is every single time window, every single slice of time, and recreating the complete network, looking at all the dyads that were engaged in events and the ones that weren't. And we're expanding our edge list to include this. So now if you're following me in my conceptual image, we started with this edge list, one column of senders, one of receivers, one of time periods. Now what we're having is an expanded edge list where we have one column of senders, one column of receivers, one column of time periods, and one column telling us whether the event occurred or whether it didn't. And that binary variable is our dependent variable in this analysis. Once we have it in this format, it gets to a logistic regression. That binary variable is our dependent variable, and we're predicting whether or not a dyad is connected at a time period. What we're able to do with REM, which makes it so cool and so powerful, is we can start linking in all types of time invariant, exogenous, and endogenous variables. So we can include time invariant stuff, time varying stuff. We can include characteristics of nodes that are constant across time, such as maybe race or parental background. We can include things that vary across time, such as income, maybe educational attainment. We can include unit invariant variables, characteristics of time itself, such as policy initiatives or interventions. But we can also include the endogenous stuff that we're often interested in. So we can include triadic closure. We can include the frequency of events that have occurred between two actors in the past. And we can interpret all of those coefficients as affecting the hazard rate or the timing to the next event. Now, the reason REM is actually able to just be estimated as a logistic regression is we use a convenient workaround provided by the data. And what that workaround is when we know the exact timing of events, we can essentially measure the network of previous relational events at all time periods before the one that the event occurred. And by looking at only the network structure before the time the event occurred, or the hypothetical changes to the network structure if the event were to occur, we're able to maintain the sequential exogeneity of the event sequence, meaning that we don't get this endogeneity problem, we don't get the feedback loops, and we can estimate it as a logistic regression. And if you guys are really hyped up about the Sienna modeling workshop, this is actually the exact same way Sienna models handle the endogeneity of events by kind of imputing those changes and then estimating the model as a multinomial logistic regression. So I'll pause here for questions, feedback, or anything else that we covered in the workshop. But just to rehash, I think the easiest way to think about a REM is entailing these two stages. The first is pre-processing the data, taking the raw data structure, elaborating it, getting it into this convenient framework where we can compare the dyads that are connected and the ones that aren't, and then simply estimating a generalized linear model to that data structure. And if we think about it that way, it's really not the most intimidating model in the world. Right? So I'll pause here for questions.
Awesome, thank you. Floor is open for questions. Perhaps just a quick one to get people started. Do you have any advice or sort of, I don't know, experience on scope and scale? So like how big, how many nodes, how long, a combination of those things? Like when is this a practical model? When is it like, you know, you better set in for a supercomputer? Like what's the scope conditions here?
Yeah, so there's a lot of variability here. So it's one of those things where the dimensionality of the data is multiplicative. So as n gets larger, as t gets larger, it's going to exaggerate the other dimension and increase complexity. Now, I will say there's kind of different ways of approaching it that can either make this model more or less tractable. So one very popular software package for REM is the relevant package designed by Carter Butts. And this is a great package for unipartite REM, especially directed sequences. If you want to allow for turn taking, for instance, Jim talked, then I talked, right? So this is turn taking in event sequence. Carter's package is fantastic for that. The limitation of Carter's package is it does all the data pre-processing under the hood. And what that means is that if you have a really big event sequence, it's going to take your network, expand it into an edge list, compute all the endogenous stuff you want on it, and estimate the model in one fell swoop and then return it to you. Now, when you're actually implementing REM, the thing that takes the longest is the pre-processing. And so doing everything under the hood in one swoop can be very, very poorly scalable to larger event sequences, longer time periods, or larger network data. Now, a second package that has less utility for turn taking, but more utility for bipartite and non-repeatable event sequences is the REM package that's designed by Lawrence Brandenburg. And the reason I like this package is it only does pre-processing. And it allows you to do pre-processing in parallel, so you can take advantage of multiple cores. And when you do that pre-processing, of course, you're still going to hit limits. If it's big data, you might have to let your computer churn for 3 or 4 days or something. But the advantage of it is once it's pre-processed, you just save the pre-processed data. And then it's in your pocket and you can do all the estimation that you want to. And so the limits you're going to encounter right now, kind of because of software availability, are going to depend a bit on what package you choose to pursue, and also kind of the workflow you choose to implement. Whether you're doing the pre-processing and estimation manually in separate stages, you can reduce the overall amount of time for larger networks. But if you have smaller networks and are really interested in turn taking, then you can still do it in one fell swoop in kind of a more tractable amount of time.
Cool, that's good advice, thanks. And if you do all pre-processing, you can then use effectively any of the event history sort of tools you prefer, right?
Exactly. I mean, you don't even have to do it with event history explicitly, right? You can use a multi-level model. You can do just a generalized logistic regression, right? At that point, it's really up to you.
Yeah, well, that's good to know.
Go ahead, Jimmy.
Yeah. So your kind of comment about it not being a particularly intimidating model once you kind of think of it in the logistic terms, I take that well, but I think of it intimidating in the other way, and that is the data needs. And so I guess my question is really kind of how robust REMs are to kind of temporal gaps in your data, would be kind of the general version of my question.
Yeah, that's a great question. And I think that's one of those things we don't have a totally clear-cut sense about yet, but I'll kind of appeal to the analogy with event history analysis on this, which is that for REM, what you really need is the proper sequencing of events. So in my mind, it's less about the overall time gap between events and more that you can recreate their approximate order relatively well. Now, the less accuracy you have in that type of order, the more difficult it's going to become. And I think of this as actually kind of being a similar issue that you encounter with Turgum, where the bigger the spacing or the less granularity you have on the sequencing of tie changes, the less accurate your network representations are going to be when you actually include them in the model. So what kind of tolerance can you really expect? It's kind of open, and it's going to really depend on the nature of the event sequence. If you're looking at an event sequence where there's a ton of activity in small time frames, for instance, kind of Carter's motivating example was communication calls between disaster responders and the 9/11 emergency. And in that context, phones were going off every other minute, you know. And so if you have an hour of silence, that's going to be a big deal. but it's largely going to be a big deal because you don't have the sequencing available for that hour of silence. Now, if you have a longer event sequence where it's more normal to have long time periods between events, beer drinking sessions with friends, maybe you go every other week or something like that, you can tolerate these longer time gaps between them as long as you still get the approximate sequencing. So I think the data demands it's a core requirement of REM. And if you have that data structure, it's really useful. The areas where I see REM being applied the most right now are kind of digital trace data is a major source of REM, official records, anything where you can actually really get that timestamp is quite good. But in terms of kind of our generic data structures, I mean, I don't think it's really plausible to expect to work with network survey data and estimate a REM to it. It's just really not kind of the structure it's designed for. I think I talked around your question a little bit, Jimmy, but I hope it kind of good. I'm glad that was helpful.
Actually, your answer prompted another question for me, which was digital trace data. I can see that in lots of sort of like electronic medical records or sort of the records that are key to a particular like space. But what about things like Twitter data or Facebook data, where you have a good detail of the amount of information on the set of nodes you've observed, but you have a tiny subset of the network that could be observed?
Mm-hmm. Yeah, so if I'm hearing you right, this is kind of about the boundary specification, right? You're only observing.
Yeah, exactly. So you know especially for something like Twitter, you probably have like perfect data internal to the set of nodes you've collected, but nothing outside of what is probably an arbitrary boundary. Do you have suggestions for how to work with that, or should we not? I can make up some ad hoc workarounds that, like, counting the number of times people are liked outside of the set or whatever, right? So you can get some external exposure indicators, I'm guessing, but I'm wondering if you've seen other opportunities or how best to deal with that.
Yeah, I haven't. I think so the cases that I've seen so far, so there are a few kind of informative studies that have given some insight to how this can work. For instance, there's a piece by Jürgen Lerner who's showed that if you subsample kind of representative subsets of dyads within a REM, then you actually get very low bias in the estimates, even for the endogenous parameters that should be a function of network characteristics. So in a hypothetical scenario, yeah, isn't it? In a hypothetical scenario like this one, if you only get a subset of the network, but it happens to be a representative subset, then you're probably in good shape. If it's not a representative subset, then I think you're going to be working in the realm of kind of a canonical selection bias. You're really only going to be able to comment on the properties of the subset that you're examining. I will say to a second point that I think is kind of related to what you're getting at, which is the question of heterogeneity in larger networks. Where rather than only having a subset of the data, you might have heterogeneity among subsets of a broader data set. And there have been some efforts to handle that, including kind of, if you know the nesting structure, then you can do a frailty model or kind of a classical kind of thing like that. But there's been some work by Du Bois and Carter Butts in a paper that was published in a computer science proceedings that use stochastic block models to detect latent communities within relational event sequences and then nest actors within them to adjust for kind of unobserved heterogeneity. So if you have a larger network and you're interested in accounting for differences between them, that's a way you can do it, even if you don't have a pre-specified nesting structure.
Okay, well, that's good to know. Yeah, it always surprises me when sampling works, because I would assume that these kinds of models, particularly for the endogenous coefficients, would require the ability to observe the rate of triadic closure, which you couldn't do well for samples. But
that's exactly what I would think too. So it's a pretty interesting result. So I will say a larger or one issue that can emerge in REM that is very closely related to kind of its roots in sequence analysis and event history is the problem of left truncation.
okay.
So this is one of those things where, in event history analysis, you might have events that precede or occur before your data set actually begins. And in REM, the reason that becomes a bigger issue is if you're not observing the earlier relational events, say it forms a triad, you start your observation window after the triad forms, all of a sudden, all the later events occurring within that triad don't get measured. And so with that type of problem, it can actually be quite severe. It doesn't actually bias the exogenous coefficient estimates that much, but the endogenous coefficient estimates get quite problematic. And I've done there's a few ways you can handle it. For instance, one is you can assign rolling time windows. So if you know how long the kind of duration of exposure is, then you can truncate your data set and only include the time windows that fit, or the observations that fit in those rolling time windows. If you don't know exactly when the time window should be binned, I've done some simulations, and one thing that turns out is stratifying by dyads actually helps a lot. So if you include a vector of fixed effects, or n-1 fixed effects, where n is the number of dyads in your sample, that can actually hold constant, essentially, the unobserved heterogeneity between each dyad. And since the endogenous stuff that you're not observing occurs before the event sequence, it can actually substantially reduce that bias. Doesn't fix it, but it reduces it by quite a amount.
That's got to require a long time sequence, right? Because you've just given up n-1 degrees of freedom each time period.
Either a long time sequence or a lot of repeated activity. Yeah.
Okay. Yeah. I'm always leery of fixed effects just because of it. They hit the power you take, but
Me too. Speaking of the choir.
Well, awesome. These are really great. Other comments or rejection? I know, Tom, you've been working with REMS. You have reactions or thoughts to some of this?
Yeah, I mean, I've bugged Scott for questions for months now, but yeah, but yeah, no, I'm actually well on my docket. Like next week is me just generating and regenerating REM measures. But one thing I'd love to hear, your advice about is, I know Lerner and Lomi have that paper about case control sampling, right? For as far as right, their whole point is that you don't need all the non-events. You can just do some multiple, and at least your base intercept is unreliable, but the networks are sparse enough that it doesn't matter too much. I guess what I'm trying to figure out, like, do you have any recommendations for best practices for case control sampling? Because I know, I've been trying to do the case control sampling sort of ahead of generating the metrics. That way, the runtime for generating is a lot faster. But I've run into issues where it's like I need to at least have like the first instance where that dyad could possibly occur, so that it knows that these two nodes are on the network, right? I've had to part of why I'm still running and rerunning this stuff is I realize there's different reconfigurations I need to do, and I don't know if you have any suggestions for the best way of the checklist of do this.
Unfortunately, no, I haven't dealt with case controlled sampling too much in my own work. So this is kind of, it's an emerging area, kind of going through what exactly you can include and what you can't include. So kind of, if I'm hearing you right, the issue you're encountering is you have a large event sequence, right? In your case, a lot of repeated activity, is that right?
Yeah.
And then the issue is making sure that you have the dyads involved at the first period of observation, but
the tricky thing is that in my network, right, people enter and leave the network, right? And so as far as calculating sort of like the history, like reciprocity and things like that, right, case control sampling, the idea is that the non-events you sample are random. As far as actually, what data set you give in after case control sampling, you always need the first non-event of a dyad, because that lets the REM package know, oh, this dyad, this is the point in the event sequence where this dyad could have existed.
Yeah, so the reason I was asking is your data is essentially really large T, but not massive N, if I remember correctly.
Yeah, it's it's about 90 nodes at a time. And I mean, it's years of sequential days, but honestly what I'm doing is I'm just doing a randomly chosen stream of 100 to 200 continuous days.
Yeah, so the reason I was asking is the Lerner and Lomi example was kind of about a kind of almost the opposite case, right? It was massive N rather than large T. And so I'm wondering whether the case control sampling is the best fix for the issue you're going through. And the reason it might not be is that if you essentially have really small counts of dyads, then randomly sampling within them, you're going to get a lot of sensitivity to whatever you include versus exclude, which sounds like the issue you're encountering.
Yeah.
Another way to do it, or think through what you're trying to do, a couple suggestions. One is if the unit of analysis is down to the day, a kind of cursory look might be to just aggregate it higher to reduce the complexity. And if you have enough activity, that should be fine. I mean, you'll want to do sensitivity tests to make sure that it's not super sensitive to your decision about how high to aggregate it. A second option might be to do rolling time windows in a slightly different sense than what I was just talking about, which is you might iterate over kind of, you pre-process the data or whatever, you have your event sequence, and then you iterate over each kind of section of the data and fit a separate model to that. And then you can combine the estimates. And if you're assuming homogeneity across the time, the entire event sequence, then your estimates should be essentially more or less the same by slicing them up that way. Because again, I think the major issue that you're encountering here has to do with the time frame rather than the sample size. So you'll have to handle it slightly differently.
Okay, yeah, the rolling time. I'll probably follow up with you on this next week. But the rolling time window idea is intriguing to me. Thanks.
You got it.
All right. Well, again, thanks a lot for sharing this with us. And for if you find yourself with this kind of data, it's a remarkable set of tools. So thanks very much, Scott. And check out his book. You should have a copy of it there to show to all of us.
Yeah, good, right? Too bad I don't get it. Thanks everybody for having me. It's been great.
It's been great. All right, let's take I think Paul's in the room. There is, yes. So let's take a little bit of a break, and we'll come right back at about. So I have 2:27 now, so we'll take a 5-minute break. We'll start about 5:02 or so. Awesome.